Hi everyone, welcome to the day 13 of Mini-Astro-workshop series 2020. I hope you people are finding these talks informative. So someone asked for a link. I did post it in the chat, the link to the YouTube playlist. Please find it there. So today with us we have Sumedha Biswas, who just recently completed a master's at University of Amsterdam. Uh, and she'll be joining her PhD soon at Radboud University. Mainly to work on multi-messenger astronomy and astrophysics in the context of gravitational waves and other electromagnetic counterparts too. And she has done her bachelor's from Christ University, and she was also a part of a program called README, which is going to briefly talk at the end of this lecture. I think it's pretty useful for people who live in Bangalore, in and around Bangalore, that particular program. And apart from that, coming to her research experience, she has worked quite a lot on dark matter uh, and also primordial black holes. So her thesis was during her master's. Her thesis was on primordial black holes using gravitational waves. As you people may have heard, there are these recent observations that were made by LIGO and Virgo detector, wherein people could not really explain some of the observed astrophysical objects, and people really think that some of these astrophysical binary black holes, etc., that they observe can be explained using primordial black holes, and it's getting a lot of attention. I mean, a lot in recent times. So I'm very happy that she agreed to give a talk on primordial black holes. And during her master's thesis, she has worked a lot on primordial black holes and how to search for them. And she has also developed a pipeline and a software package, everything, to actually detect and do parameter estimation of such objects. And she was also part in the past worked at ICTS Bangalore, where she worked briefly on numerical relativity and looked at Einstein Toolkit, which is the most famous open source software for dealing with Einstein equations. And she has also been part of a lot of outreach activity, and she writes some really nice articles. And she has attended a lot of conferences and workshops and given talks. So she has a lot of experience in giving talks too. And last but not least, she is also part of the LIGO Virgo collaboration and the European Gravitational Observatory Consortium. Uh, yeah, with that, Sumedha, you can kick it off.
Right, okay. Thanks a lot for the introduction. So everybody, hi. So as you can already see the slide, I'll be talking about primordial black holes and how we can detect them using gravitational waves. So, sorry, this is, yeah. So the basic structure of my talk will just be, is basically divided into two. So in the first part, I'll be talking about primordial black hole theory. And in the second part, I'll be talking more about how to detect them and more about what I've been working on. So for the theory part, of course, I'll obviously talk about what these objects even are and how they came to be. So some formation mechanism theories, and I'll also briefly touch upon the concept of primordial black holes being really good candidates of dark matter. So yeah, so please feel free to interrupt me if you have a question at any point. Yeah, so what exactly are primordial black holes in the first place? So these are basically black holes that formed in the early universe. And by early, I mean just a few seconds right after the Big Bang. So that's what makes them really, really interesting, because for a fact, we know that they formed from non-stellar evolution mechanisms. And what I mean by that is previously, for example, we've looked at stellar evolution theories, and we know that when massive stars die, they usually produce a black hole. But obviously, a few seconds right after the Big Bang was not enough time for a star to have been born, to live its entire life, and then die to produce a black hole. So we know that these definitely come from different mechanisms. And of course, we still don't know the exact theory. And that's what some people are really looking into at the moment. Another interesting aspect, which I'll also mention much later, is the fact that they're predicted to exist over all mass ranges. And this is an interesting point in terms of detection. And at the end of the day, these objects are still hypothetical, as no detections of them have been made so far. And that's exactly what we're trying to change. So in recent times, there have been a lot of papers regarding primordial black holes. people have been studying about it in all kinds of aspects. The fact that they're dark matter candidates, the fact that they could also form binaries with other compact objects. And there were also some recent relevant detections which have really brought the spotlight back on primordial black holes, which I'll be mentioning a bit later. So the point is that, yeah, these are very relevant for the time being, and it is worth studying them right now. This one, for example, I thought was really interesting. So I don't know how many of you know about Planet 9, but Planet 9 is basically a hypothetical object that we think exists within our own solar system. And we think it exists because of the orbits of all the other planets. They are in such a shape that we think that there should be another object which is sort of having an effect on the nature of their orbits, rather. So in this particular paper, they introduced the concept that maybe Planet 9 is a primordial black hole. And of course, the paper is pretty technical, but what's interesting is the fact that they included this image in it. And if you look at the caption, sorry, if I move it, covers it up. But anyway, this is an exact scale image of a five solar mass primordial black hole. So it was really talked about when they published the paper. So that's, yeah, that's just an interesting thing. So I'll be jumping right into the theory of it. So the absolute basis of primordial black hole formation is basically from density inhomogeneities in certain parts of the universe. I'll explain what that means in a bit in more detail. And so in a way, it means that there are areas where the density tends to clump together, and this basically leads to a gravitational collapse. And once that happens, you have a primordial black hole. So that's what we think is the basic idea of their formation. But the different theories basically arise when we try to wonder why these different density inhomogeneities even come to be. So very broadly, they're divided into two. So you have the inflationary scenario, which I'll be discussing in detail, and you have the non-inflationary scenarios. These are just a few. There are some more. I will not be going into detail about these, but I have included a list of papers in the resources list on the GitHub page. So you can check that out if you're really interested. Okay, so before talking about it, let's just go back to what the timeline of the universe looks like. So we have the Big Bang over here, and we see that the universe starts to inflate around this point. And the whole point of inflation, obviously, is that we want is to create a homogeneous and isotropic universe the way it is right now. But primordial black holes were basically formed around this region between the Big Bang and around the time when inflation started and even after. So that's basically the era that we're looking at particularly. So what happens is that inflation leads to a homogeneous universe, like I said, and the amplitude of the density fluctuations in a perturbed region. So by that, I just mean the way it's being clumped together in one region. If that's greater than a certain value, then primordial black holes form. Of course, there's a lot of maths involved, but it's not too important as a layman to understand all the maths. It's just important to understand the concept. So that's why I've omitted most mathematical terms from this presentation. So this video basically, even though it's about 100 years after the Big Bang, it basically shows you how the matter tends to clump in certain regions. So you see the regions which are basically turning darker, and that's basically the parts where structure is being formed or material is just coming together. So those regions are basically predicted to be the regions where primordial black holes could have formed. So this is 100 years after the Big Bang, mostly because I couldn't find a simulation from right at the beginning of the universe. So 100 years after the Big Bang is around this region. So right before the radiation era, somewhere here. So that's basically what we looked at. And of course, this also forms as an open problem because so a lot of people work on creating these cosmological simulations of the universe. And there's only so far that we can look back at. And so far, there hasn't been a simulation of the early universe, which shows a few seconds right after the Big Bang, which might be interesting, especially in terms of primordial black holes. We might actually get an idea of how they're formed. Okay, so you saw that they were basically being created, or they were forming in the inflationary era, but they actually tended to form binaries in the radiation-dominated era when the universe cooled down a bit more. And they basically formed these eccentric binaries when they approached each other. But primordial black hole binaries can also definitely form in the present universe. And this is because we think that primordial black holes are freely moving through the universe. And of course, there could be some which are interacting with other primordial black holes while they're traveling through the universe. But in another way, they're also predicted to be clustered around these large dark matter halos that usually surround galaxies. So that could also be a place where two primordial black holes tend to interact with each other and form a binary. And in terms of detection, that's exactly what we want to detect. We want to detect a primordial black hole binary. So the main reason for that is because primordial black holes are obviously really, really small, as you saw. And the gravitational waves from them would be very weak. So if we have a binary, there's a much higher chance of us being able to detect it. So, of course, this is still an open problem. We don't know how primordial black holes even formed. And this is, a lot of people are really studying about this. They're developing models and methods, and inflationary cosmologists especially are really concerned about this because they think that once we know how these came to be, it would shed some light on the early universe. Okay, so next I'll be talking about how about primordial black holes as dark matter. So these are really good candidates of dark matter. They're very debated as well. So while some people think that maybe all of dark matter consists of primordial black holes, some others think that definitely a percentage of dark matter consists of these objects. But generally, dark matter consists of two different types. So you have the WIMPs, which are basically the weakly interacting massive particles. So these are hypothetical particles so far, which we have not detected yet. And these are beyond the standard model. So that's a different domain altogether. But then you also have the MACHOs, the massive astrophysical compact halo objects. And primordial black holes are basically what we call MACHOs. In another interesting paper, this was, I think, from 2016. So as most of you know, gravitational waves were detected for the first time in 2015. But in 2016, this group from Johns Hopkins University basically published this paper about whether LIGO had already detected dark matter. And their main claim was that everything that we were seeing with LIGO was actually primordial black holes and primordial black hole binaries. So so they go on to talk about the constraints and the different sensitivity issues that could possibly lead to this claim. Honestly, I haven't seen another paper related to this in the years that followed, so I don't know if people are actually pursuing this, but it was still an interesting claim nonetheless. Okay, so now that we've more or less understood some stuff about the theory, we can probably jump into the detection, and this is also the main part of my research and what I've been working on for almost over a year now. So as I mentioned previously, primordial black holes are predicted to exist over all mass ranges. And this is really, really important because that means no matter what we're detecting, no matter which mass region we're looking at, the possibility of detecting a primordial black hole is always there. And that's insane. So that's something that we decided to focus on. That's something we based our entire study on as well. So for example, a pen cap roughly weighs a gram. I Googled this, I did not know this before. And a primordial black hole could be 10,000 times less than the mass of a pen cap, but it could also be about 100,000 times heavier than the mass of the sun. So that's a huge range. And this means that we can look at literally any region at all and wonder about primordial black holes. So very broadly, what we did was we divided primordial black holes into roughly two big regions. So we have the subsolar mass region, which is below 1 solar mass, and the supersolar mass region, which is anything above 1 solar mass. So the good thing about subsolar mass regions is the fact that no other astrophysical theories really predict the existence of any objects here. And so that basically means that if we were to make a detection, it would be a primordial black hole. Of course, this is barring, I think, Surendra's upcoming paper where he thinks that we could also possibly detect heavy neutron stars. But at least from our perspective, we think that if we made a detection, it would most definitely be a primordial black hole. And in the supersolar mass region, the main issue becomes differentiating it from other stellar black holes or other objects for that matter. So that's something we need to focus on as well and address. So for the rest of the talk, it's also divided in a very similar way. So we have the subsolar mass region. So what's the main idea of considering the subsolar mass region is what I just said. So you have most of the black holes in this region I think the lowest detected so far has been 5 solar masses or a little above that. And neutron stars are usually predicted to exist between 1 and 2 solar masses, and sometimes a bit heavier ones are between 2 and 3. But effectively, this means that we don't see anything else below 1 solar mass. That region is completely blank. So it is a good place to actually consider the possibility of primordial black holes, especially since they exist over all masses. But there is an issue. It's not as straightforward as it is. It's not as simple as just looking at below 1 solar mass and expecting a detection. So if you look at this video here, so all of these events, except the last one, are binary black hole mergers. And those waveforms are much, much faster. So let me just pause it here. So the beginning bit of the waveform, that's the part when the two black holes are basically spiraling around each other. And once you see the peak, that's when they merge, and then you have the ring down, or the final product. But in the case of binary neutron stars, which is the last case, GW 170817, you see that the inspiral phase goes on for a very, very long time. And this is because of how low their masses are. They take a longer time to inspiral, they take a longer time to actually combine, merge. Yeah, that's what I was looking for. So they take some time to do that. And this is an issue because that means we need to analyze waveforms this long. So if I skip all the way to the end, because this is pretty long, you see that at the end, somewhere here, they tend to have a tiny merger over there. So we are dealing with very long waveforms, and this does make it very, very expensive. So even if you're using supercomputers with, I don't know, about maybe 60 TB RAM space, it's still very, very high, the costs, and it takes a very long time. So that's further supported by this expression from this paper in 99. So usually what we do is we consider different, so a lot of you have attended the Introduction to Gravitational Waves seminar before. So we do something called as match filtering, where we consider different templates of gravitational waves. So we would need more templates, basically. So this n over here is basically the number of templates, and mmin is the minimum mass that we're considering. So naturally, the lower the masses we consider, the higher the number of templates we need, and hence our computational costs definitely go up. So it's not as easy and it's not as straightforward. And this is an issue. So we don't really know how to, like straight away, we don't know how to use LIGO and Virgo to actually detect subsolar mass primordial black holes. There have been some subsolar searches in the past. This is from LIGO's first observing run back in 2015, and then the second observing run. You can check these papers out there on, you can easily access them on Archive or NASA ADS, but I'll give you a spoiler, they don't detect anything at all, completely null results. So they think that a lot of it is to do with the sensitivity of the detectors, and we need to improve our own techniques by quite a bit. So this is definitely an issue, and we don't really know how to, a lot of people are working on this at the time being, about how do we make this more computationally efficient, and effectively how can we actually probe the universe better. So this is, I would say, a less physicsy problem. It's more of a data analysis or a big data problem. So lots of people, lots of engineers as well are working towards this. There is one method that I did work on, which because of its complexity, I omitted it from the main presentation. But if anyone's interested, I did add it as extra slides, so I can definitely explain what we think a solution might be. Okay, so now we can move into the supersolar mass range, which is personally more interesting to me. So by supersolar, I mean anything greater than 1 solar mass. So for this study, we were basically trying to focus on the lower mass gap region. And the lower mass gap is basically in this region between about 3 and 5 solar masses. So this basically arises because black holes, we don't see black holes below 5 solar masses usually, and neutron stars are usually between 1 and 2. And if it's really, really heavy, then maybe above, between 2 and 3. But what this effectively does is that it produces this gap right there between 3 and 5 solar masses if you're being conservative, but you can also consider it as between 2 and 5. We don't detect anything in that region, which is weird, and it's pretty mysterious, and scientists have been wondering about this for a while. Recently, there were some very relevant detections here, which I will mention towards the end. But we decided to focus on the mass gap, particularly to look for primordial black holes. But of course, the main issue is that theoretically, black holes can exist in the mass gap. It doesn't go against theory. It's just something that we don't observe. So the issue that we have to deal with is is how do we distinguish these primordial black holes from astrophysical black holes, particularly. So this is obviously an open problem, and this is something that people have been wondering about for a while. Srinath, do you want to take a break now? I think it's a good logical point.
Yeah, I think the question that one asked is how do we distinguish between astrophysical and stellar mass black holes and primordial black holes?
Right, yeah. I mean, I'll mention what we try to do after the break, basically.
Okay, cool. So it's a question from Pramitesh. Pratmesh is asking how do we actually weigh black holes?
How do we actually weigh black holes?
Yeah, we will get the mass of the black holes, or I think weight of the black holes. Yeah.
How do we get them? I don't know. It's a lot to do with parameter estimation. How do they weigh it? That's a weird. I'm wondering about this myself. Do you have any answers as well?
Yeah,
I know that you use parameter estimation to actually look back at black holes, but I'm not sure what they actually do there to get the mass.
I think it's all in the geodesics. So the way you actually even measure the mass of the sun, obviously you can't go and put a weighing scale beyond, below sun and measure it, right? So we understand it from the Keplerian laws. So if you actually can understand orbital dynamics, and from that one can understand the input parameters that are required to explain your observations, which are basically trajectories around these objects. And from that one can understand the mass. Like supposing you have a given gravitational signal, to get that resultant gravitational signal, only certain parameters like a certain mass, certain spins, only those can actually explain your gravitational signal. So from that, we measure the mass of the black holes. But the actual definition of mass of black hole and everything, it's very complicated in general theory of relativity.
Yeah, that's what I thought he was asking.
But we use something called ADM formalism. If you're interested, you can just Google it. ADM formalism. Yeah. Next.
But yeah, I think, okay, sorry, that was just an add to that. But yeah, go ahead.
Divyanshu is asking, would the small mass black holes would just fade away, die out as a result of Hawking radiation? Or is it that can we detect them before the decay, or black holes doesn't decay at all?
I think they can decay, but I think we can also detect them right before they do decay. Anything to do with Hawking radiation stuff, it's just we know so little about it that kind of hard to answer the question. But it is a possibility. I wouldn't completely say it's not a possibility at all.
Next, Jayesh is asking, do primordial black holes only exist in binaries? If not, could there be an insight from primordial black hole astrophysical black hole interaction or mergers?
Oh yeah, definitely. So that's what I was trying to show in the beginning. They do form binaries much later. Where did it go? Yeah, so this was if they form binaries in the early universe, and in the present day universe, they can also form binaries. But obviously, when they form, they're single objects. But then they interact with each other and they tend to form a binary. And sorry, what was the second part of the question?
The second part is similar.
Oh, right. Can we have different interaction? Yeah, we can, definitely. That's also something that people have been studying right now. So I think there was this one paper about the interaction of a primordial black hole with a neutron star system somewhere here. I probably should have put this in a better way. Oh yeah, here, this one. Neutron star primordial black hole merger. So yeah, that's definitely a possibility. They are also black holes at the end of the day. You have to remember, like the structure is similar. They're just different because of the way they formed.
Yeah. Like Sharma is asking, will 21 centimeter cosmology help us in any manner to fill some gaps about primordial black holes?
Will what help us fill the gap?
21 centimeter cosmology.
I guess. I'm not very well versed with that, so I don't know. Honestly, I don't know, but I think so.
And so Adesh is asking, so primordial black hole is a mathematical model devised as a precursor to understand the origins of dark matter?
I think that's a like a roundabout way of looking at it, because we do know that these objects exist. So I think it was first that, I mean, we first thought that primordial black holes exist, and then we thought, okay, you know, they are also dark matter candidates. But I think effectively it's the same thing. No matter which way you look at the thing, it's still that at the end of the day, primordial black holes are theorized to exist, and they are really good candidates of dark matter. So it goes hand in hand in a way.
Yeah. And next, Raj is asking, what are the major differences between primordial black hole evolution and stellar evolution?
So stellar evolution, so I mentioned this initially. So stellar evolution is usually, so you have a really massive star, and that lives through its entire life, and then it dies to produce a black hole. So we refer to those as astrophysical black holes or stellar black holes. But primordial black holes didn't form from stars at all. They formed from completely different methods of mechanism methods. Anyway, so they did not form from stars. So that's like the main difference right there. And the main reason for that is the fact that they formed so early in the universe.
I think we also expect differences in like the spin distribution, the mass ratio.
Yeah, I'll be talking about that in a bit more detail.
Oh, okay, sorry for that. Yeah.
No, it's fine.
Next, Devarshi is asking, is there any way to say that the detection is an inflationary or non-inflationary one? Similar to inflationary ones, do we expect primordial black holes at all mass ranges from non-inflationary scenario too?
Yeah, if they formed in the present universe. But the thing is that no matter, I think, if we were to detect a primordial black hole, we sort of know that it is coming from the early universe. It did form during the inflationary era or the radiation-dominated era of the universe. So we do know that. But the difference is that if we were to detect one at maybe very low redshift values, that means it's nearby, right? So that just means that the primordial black hole has traveled so far to somewhere nearby which we can detect. But effectively, they are all of inflationary origin.
But he's also asking, is there a way to differentiate between the two of them?
I'm not sure what you're trying to differentiate exactly, because, for example,
Between inflationary and non-inflationary.
But they are all inflationary, right? I mean, unless you mean that, okay, so if you're detecting something from the, I don't know, like years ago, your redshift values would be very different. So I think that's the main differentiating parameter. But at the end of the day, they all formed at the end of the, at the beginning of the universe.
Okay, let's see, Devashi raise his hand. I'll try to unmute.
Hi, Sumedha. That was a really lovely talk that you've been giving. Yeah, to clarify on my question, so I think you showed a slide where you said you could have non-inflationary scenario where you have like from cosmic necklaces and
okay, that's
bubbles.
What you, right?
Yeah. So I was trying to think whether you can differentiate like if there is a detection, can you differentiate between these scenarios? And also, can you have like all mass range black holes for the second scenario, the non-inflationary scenario?
Right, yeah, so this is something that some early universe cosmologists look at. So what they do is they construct a power density spectrum, which it's a bit complicated, but basically tries to show the nature of the fluctuations from when they formed, basically, and they try to backtrack that. I'm not sure how they would do that with gravitational waves exactly, but I think there is a method to do it. I mean, the problem is that no one's done it before. Because we haven't made a detection, obviously, and I don't think anyone's really focused on trying to differentiate them. But it should be a possibility, I think, because of that power spectrum. I decided to omit it from these slides because it wasn't too relevant. But yeah, I think it should be a possibility.
Okay, thank you.
Yeah, just to add something to what previously someone asked on the vanishing of these primordial black holes, I just wanted to be sure the temperature of the black hole, the Hawking radiation, does inversely depend upon the mass. So as you decrease the mass, the temperature is going to increase rapidly. So it's going to vanish pretty fast. Yeah.
Yeah, but I mean, I think they also asked if we can detect it before it does. So I think that they'll do that. In theory, you could. I don't know if you can do that in real life. But yeah, it's possible.
So next is from Shubham. Maybe you'll answer it later, but for primordial black hole mergers, how do actually difference in GW waveforms from existing astrophysical black hole mergers? Like in what magnitude scale?
Yeah, I will explain this a bit more in detail. So if you still have a question after the second part, then ask me again and I'll try to clear it.
And Manas is asking the recent merger event where we were not sure about the second binary. Could that have been a primordial black hole?
Yes, I totally think it could be. So I've added the relevant gravitational wave detections towards the end, and I mean, there are some certain parameters in both of those detections, the low mass gap detections, that might comply with primordial black holes. So that is something that's really interesting. I know some people are working on that right now, but it is possible, and I personally think it is. But of course, there are many theories to it.
Yeah. Next, Pratmesh is asking a general question. If the source of gravitational wave was as close as near to our solar system, would it be any different from the waves that we measure now in LIGO?
I mean, that we measure in with LIGO? Is that the last part?
Yeah.
Not exactly. They would be stronger signals though, so it should be well, easier to detect them in that sense. So the closer the objects are and the closer the gravitational wave producing events are happening, we detect stronger signals. And the farther away that they are, the waves become the signals become really faint, so it becomes harder to detect. But generally, if you look at the wave itself and the nature of the wave, it shouldn't be different at all.
Next, Tasmi is asking again, can you please again explain how the primordial black hole formed?
Right, yeah. So okay, let me just look at, go back to that video. I think even though this isn't exactly for primordial black holes, it kind of gets across the idea really well. So basically what happened right after the Big Bang, and once the universe started expanding, inflating or expanding, yeah, is that some matter and some particles basically came together and they started to clump together basically. So in the darker regions in this video, for example, that's the regions where the matter was being clumped together. And eventually, overall, that's if you move into the evolution of the universe some more, these are basically what finally form the structures of the universe, like galaxies and stars and all of those other things. But the point is that if they reached a certain critical limit, they basically collapsed gravitationally. And once they did that, a black hole formed. So that's what we think is the basis of primordial black hole formation. I hope that answers your question.
If not, you can try to raise your hand and ask the question. Yeah? So there's this general question which one person keeps asking. Is Manish is asking, can you please briefly talk about the discovery of the black hole at the center of a Milky Way galaxy, for which recently a Nobel Prize was given?
Yeah, I don't think I'm too qualified to be giving you that talk. But yeah, I mean, again, what do you want to know exactly? I think that might be more helpful. Generally, it's a very broad question.
Yeah, Manish, you can raise your hand. I'll try to unmute you and you can ask the question.
Hello.
Yeah.
Yeah, am I audible?
Yeah.
Yeah, ma'am. I want to know that how this black hole means we have discovered the black hole at the center of the Milky Way galaxy. So means how it got discovered? Means is there any gravitational lensing is used or anything? Yes, means the technique they have used.
Yeah. Did you see the video that they showed at the Nobel Prize ceremony, whatever, the announcement, basically the press conference?
Yeah,
So
yeah.
so that basically is a lensing technique. So they looked at the star trails, star tracks, whatever. So basically the motion of stars around the center of the galaxy, and they realized that it was a bit weird, and something was definitely there that was affecting the motion of those stars. So that's primarily what they looked at. But the exact method, yeah, I'm not an expert on that. I'm sorry, but yeah, I do know that that's what they did.
Okay, ma'am. No, thank you.
Yeah, so Divyanshu has asked the question previously on fading of black holes, because he wants to know, yeah, small black holes may fade out pretty quickly when they form, Therefore, maybe there is a limit to the small mass primordial black holes that we can actually hope to detect.
Okay, wait, let me think about this.
Yeah, these are really good questions.
Yeah, I guess in a way you could say that. So what you're basically suggesting is that because of Hawking radiation, some of the lower mass stars, lower mass black holes probably cease to exist before we can actually detect them. Is that?
Exactly. Yeah.
Yeah, that does make sense in a way, but what is the difference? I'm just trying to imagine what else is really different between primordial black holes and stellar black holes that might contribute to this whole theory. Yeah, I'm not sure actually. I would probably have to look into that. That's a really good question though.
Okay, then those are all the questions as of now. I can continue.
Right. Where was I? Right, okay, so this is basically where I stopped off. So the main open problem that I've been trying to address in recent times is something that we're working on right now, is how do we actually distinguish an astrophysical black hole from a primordial black hole. So what we did was we basically set up a kind of framework and we're still working on it, and we're actually working on a paper regarding it right now. So I'll just give you the basic outline of the framework in this slide, and I'll get into the details in the next couple of slides as well. So the very first thing that we should be doing, or that we think we should do, is we should choose appropriate astrophysical and primordial black hole models to describe the lower mass gap region. Of course, like this whole framework is, I mean, I will say lower mass gap over and over again because that's what we're particularly looking at, but it also applies to all other mass ranges. So, so yeah, that's the first step. So by models, I mean, yeah, in the next slide, I'll probably show you an example that might be easier to explain. But the next step is basically we use these models and we generate fake gravitational wave signals or injections, as we call it, and we inject them into the detectors. So the idea is that for the gravitational wave detector like LIGO and Virgo, this is a real signal. So that's what we're telling it to do. And once we actually inject it like that, we run a parameter estimation analysis using Bilby. So if you attended the talks on day 5 and 6, maybe you've already come across this. But just as a gist, the main idea of using Bilby and parameter estimation especially is, so let's say you have a gravitational wave detection. So we have LIGO Virgo, it makes a gravitational wave detection. So that's great. So you see a signal that looks like a gravitational wave, but how do we know what actually formed this gravitational wave? How do we go back to the source? So that's what parameter estimation basically helps you do. It's a whole Bayesian analysis technique which helps you get back to the source. So in that way, we can find out about the masses, we can find out about the spins, how far away is it from Earth, where in the sky is it located, or a bunch of parameters like that. So that's basically what we use parameter estimation for, to trace back a signal to its source. So that's the third step that we try to do, and we try to do this with our fake signals, remember. So that's the third step, and finally we try to figure out which model is more likely given our conditions. So by model, I mean what we did in the first step, the models that we chose there. So I know this seems maybe a bit too complicated, but I'll explain it a bit better in the next couple of slides. So for example, the first step that we have to do is to choose the model. Again, this was a test run, and this is basically our prior knowledge. This is the information that we know, but the detectors do not know, and that's really important. So we considered basically 3 different scenarios. So if you look at the legend over here, so this is basically a very, very simple power law in just one parameter. This is the primary component mass, M1. And we considered a very simple power law. So that's what a model basically looks like for astrophysical black holes. That's what we considered. We have a similar one for, so as ABBH stands for astrophysical binary black hole, PBH stands for primordial binary black hole. So those are the abbreviations we gave it because well, they're really big words to say otherwise. So these are the 2 different scenarios that we consider. And then we also considered a mixture model where we have 20% of PBHs and 80% of ABBHs. So that's basically what you're seeing here. So on the x-axis, you have M1 in terms of solar mass. And on the y-axis, you have the probability of M1 in, not the probability, the prior. So basically this quantity over here, the thing that you see in the legend. So this is the information that we already have. This is what we think the lower mass gap regions should look like for these populations particularly. And again, the detector does not know this information. So then we basically generated fake gravitational wave signals or injections. So essentially we simulated these gravitational wave populations. So we considered two different models. So the Astro model that you see over here, that's basically 100% astrophysical, and so that doesn't range in the lower mass gap. It's from 5 to 10. And then we also considered a mixture model, which is basically the 20% of PBHs and 80% of ABBHs. So it's just a mix, and that's between 3 and 10 solar masses. So in these plots, you're basically seeing the distribution. So you have M1 and M2, and you see what the number of signals that we have in those regions, basically. So I just added this plot to just give you a better idea of what it looks like. So we did this, and the next step was to basically run the parameter estimation analysis. I won't get into the maths of it. It's not too important to understand the idea here. So the only thing that we finally wanted to do was calculate something called as the Bayes factor. So the Bayes factor basically tells us which model is more likely. So this is, if you see this expression over here, this is basically telling us how likely is the PBH model over the ABBH model. So for example, if this value were to be maybe 8, that would mean that the PBHs are 8 times more likely than the ABBHs. So the primordial black holes are 8 times more likely than the astrophysical black holes in that certain mass range given the model that we chose. So this is the idea. This is what we want to finally calculate. And based on this, we want to also compare it with what we know, with our prior knowledge, with the knowledge that we have and the detectors don't have. We want to compare it. And we want to see which model actually seems to perform better, which model seems to explain this region better. So that was the whole idea of the framework, basically. And so this is just a test run that we did with that simple model. So we calculated the PBH Bayes factor in the lower mass gap specifically. So let me just explain this plot a little bit. So blue one is the Astro model, which I showed you in that plot. So it's 100% astrophysical. And the mixture model over here is, again, 20% of primordial and 80% of astrophysical. So, and on the y-axis, you have the Bayes factor for PBHs versus ABBHs in that sense. So this plot is technically correct. So what it's telling you is that neither model is being preferred. Both of these models are giving you negative values. That means neither the astrophysical model is preferred in this sense. But for example, if this Bayes factor were to be reversed, if we had ABBH on top and PBH below, it would mean that this plot would just be flipped. So the astrophysical model is basically preferred because it has a negative value. That's the main idea. But of course, this is a test run. Now we're trying to improve our techniques and probably use more complicated models so that it's much easier to make that distinction. Also something that's, so this is what I was talking about before. So there have been some recent relevant detections in the lower mass gap. I don't know if you can see the question marks over here, but we have detected something in the lower mass gap. So it was a huge deal and everyone was very excited about it. So these were the two events. So GW 190425 and GW 190814. So I don't know if you know how these are named, but usually it's just the date. So this is just 25th April 2019. That was the date of detection, and similarly for the other one. And in this table, I've just listed the parameters that I think actually point towards a primordial black hole detection. So for example, let's just consider one over here. So you see that M1 is actually also touching 2.5 solar masses. Also, another important thing to note is that we haven't detected electromagnetic waves from either of these events, which would usually normally mean that it's a neutron star merger, but we haven't. So that's why this has been of more interest, because we don't really know for sure what these objects are. And it does also touch the lower mass gap over here with 2.5. And in the other event, we have a 2.5, we have 2.67. So it falls right there. And so potentially, it has potential to be a primordial black hole, basically. And something else to consider is the mass ratio. So usually astrophysical systems tend to have very high Q values, but in this case, we see that they're very low. so which could also point towards the fact that it's not astrophysical. And then we have the spin parameter. So primordial black holes, because they formed so early in the universe and because they've been traveling through the universe for so long, it's kind of predicted that they'll have very low spin values, mostly because they've lost most of their energy while traveling. So they should have approximately 0 spins. But there is one exception. If in a case where these primordial black holes interact with other objects, and they merge or things like that, so they could also have spin values that way. But essentially, normally we think that they have low spin values. And finally, the redshift, I briefly mentioned this before. The main idea is that if we're detecting something very, very far away, the redshift value should be huge. But this isn't a very good parameter to just distinguish between astrophysical and primordial black holes, because as we discussed already, that they could also exist around us. But it is a factor to take into account nonetheless. So essentially, this is an open problem again. How do we actually explain the lower mass gap? How do we explain these recent relevant gravitational wave detections? Or what are these objects even? So a lot of people are working on this. Surendra himself is working on this as well. But of course, the next step to this entire process, this entire framework and everything that I just said is we need better PBH models. Ideally, if we have a really, really good PBH model, we would get really good results. And at some point, if you have an accurate model, you could also very confidently make a comment about the existence of primordial black holes in the first place. So that is, again, at the end of the day, this is a big open problem. We don't even know if these objects exist, but there is a good possibility, a lot of people are actually looking into it, that these objects do exist, but it is an open problem. Okay, so that is basically the end of my technical talk. I wanted to talk about base and REAP. So Surendra suggested that I add this. I don't know if some of you are from Bangalore, but if you are, this is probably something that you should be looking into. So BASE is basically the Bangalore Association for Science Education, and it's at the Jawaharlal Nehru Planetarium here in Bangalore. And it's interesting because this is a place where many talks, many shows, many workshops, a lot of different things happen here. And it's a really good place to actually get to know the scientific community in Bangalore. And another interesting point to note is that BASE was actually founded by Professor C.V. Vishweshwara, who is also called the Black Hole Man of India. In particular, BASE hosts this program called REAP. So you can check out the link later. But REAP is basically Research Education Advancement Program. It's a whole program that lasts for 3 years, and it's mainly targeted for undergraduate students. And usually the idea is that there are classes on various advanced topics and subjects during the weekends, so things like vector calculus or electrodynamics, quantum mechanics, observational astronomy, all of those topics. So you have professors from a lot of these great institutes coming during the weekends and actually trying to teach you. Some people also do experimental work at the labs. I personally didn't do this, so I'm not too sure about how this works, but it is an option, I do know that. We also did a field trip to the Kainubapu Observatory in Kavlur to do some optical spectroscopy and things like that. That was also a very fun trip. Generally, at the end of each year, there are exams, and they are very strict about it. So at the end of every year, some people pass and they move on to the next year. And if you do that, then you do get a scholarship from the government of India. So in my year, for example, about 100 people started the program, but only 6 finally finished the 3 years. And also, if you're a final year student, you get to do a research project at one of the related institutes. So I did mine at ICTS, for example, as Surendra mentioned initially. And yeah, thanks for listening. If you have questions, please let me know.
Yeah, guys, so you can either post them to the chat or raise your hand. So Raj has a question in timeline slide of the Big Bang. Did primordial black holes start forming before or after quark epoch?
Sorry, did primordial black holes start forming when?
Before or after quark epoch?
Oh, around then. So they started forming like as soon as the universe started expanding. So from this region all the way to the, yeah, this whole region basically they were forming.
Okay. Next, Shubham is asking, since no EM counterpart detected for NS merger except for one, so how we actually looking to set some limits or some theory or models to actually differ these NS mergers from PBH mergers?
So the waveforms look different. That's the main difference. So where's that slide? Sorry. Yeah, okay, so this one. So in the video here itself, you see that the waveforms look different. So if you actually look at each and every single waveform, for example, waveforms between binary black holes and binary neutron stars are very different because of their nature. And that comes from numerical relativity, that comes from general relativity, even higher up. So similarly, between binary neutron stars and primordial black holes, they should be different. But it's also a really good point because that is also something we've been talking about. So we've been focusing on trying to differentiate astrophysical black holes from primordial black holes, but we could extend it to also be, to differentiate between primordial black holes and neutron star mergers. So that is the next step. So yeah, that's a good question.
Yeah, Shubham, you can talk.
Yeah, okay. Yeah. Thank you for the wonderful talk, and thank you for the answer. Yeah, that I got, like we can differentiate, like for now, from the BH mergers and neutron mergers from these waveforms like you are showing. But in the slide where you were showing the data of GW detected of neutron star mergers like 190814. So there you said like it can be a primordial black holes, and we are like in a doubt like how to be sure, be very sure. Yeah, this one. So I'm asking regarding this, like in this the GW 190425, the secondary mass and primary masses are like on the same ranges you are saying for the lower solar masses for primordial black holes. So how we are looking actually for differentiating both of these?
Okay, so there are a bunch of things you could do. For one, so the mass models I already talked about, not mass models, but any models for that matter, when we're discussing this whole framework and everything. The models of binary neutron stars and primordial black holes will be different because of all these parameters. So this is only some of the parameters. This is not all of it. For if you were to differentiate between them, both of them would have different expectation values. So you could basically incorporate all of them into a model and try to use that to be able to differentiate it. That is one thing you can do. Additionally, if you want to get more theoretical, you could go all the way back to GR and inflationary cosmology and try to actually derive the equations for both of the scenarios, and they would be different. I haven't derived it, so I cannot exactly show you an expression, but they will be different because of a number of factors, which again, consequently would basically make the waveforms look very different. So there are ways to differentiate objects even if you don't have an electromagnetic counterpart. That's not the only way to distinguish, basically. That's what I'm trying to say.
Yeah, okay. Yeah, sure. Thank you.
Yeah, guys, any more questions? You could always post in the chat or raise your hands. So Sumedha, I remember you saying if you had time, you would go to your extra slides and explain us something. I forgot what that was.
Oh, that was for the subsolar mass region. Wait. Yeah, I was gonna. Sorry, 1 second. It's not showing up. Yeah. Sure. Okay, so the basic idea of this was trying to address this problem that I mentioned here, that they are very long waveforms, that they have very high computational costs, and how do we actually efficiently try to detect something in the subsolar mass region. So before I actually talk about what we try to do, I'll just give a quick reminder of the basic steps of a gravitational wave detection. So usually what we do is we generate something called as template banks, and you can consider them as matrices, for example, where each row is a gravitational wave signal or a template. So these templates are usually generated from theory. These are not observations, but these are theoretical signals basically. And in a template bank, each row is that one signal. So we have these big template banks, which we use for the entire analysis basically. The second step is performing something called as singular value decomposition, or SVD, The details are not 100% important here, but what is important to understand is that this helps us reduce the computational costs because it helps us reduce redundancy. What I mean by that is, for example, in the video of the neutron star merger, you saw that the waveform is very, very long. So if you have a template bank of binary neutron stars, for example, we would have to deal with very long waveforms and very similar data over and over again because the inspiral phase is not too different for most of these detections. So we would have to basically reiterate over and over again. Even for a waveform that long, we don't need to look at it entirely. We just need the last part basically. So it helps. So SVD basically helps us reduce that redundancy. That's what it's basically doing. And finally, we perform match filtering, which is what I was trying to briefly say earlier. So this sort of basically gives you a very good intuitive idea. So the blue line over here is the data that's coming into the detectors and the gravitational wave detectors. And the orange one is the template from the template bank. So all we do is we take the detector data and the template that we know should look in. So we know what a template should look like. We know what a template is in that sense. So we try to put them on top of each other. So we overlap them and we see if there's a match. So for example, in this one, there is a match right here, which means that, yes, okay, this is a gravitational wave detection and this is what we think it is. So that's usually the basic main steps of a gravitational wave detection. So what we were trying to suggest as a solution was something called as random projection-based angular value decomposition, or RSVD. So the main idea over here is if you look at this figure, the one on top over here is the original template bank or the template matrix. And what we basically see here is, so you can basically imagine a gravitational wave signal over here. And so that's why we have NT on the y-axis. So there are NT number of templates. And each point on the gravitational wave signal is NS. That's a data point. So that's the number of data points that we have. And what RSVD basically does is that it transforms this original template matrix and reduces it in dimension to a reduced template matrix like the one we have over here. And for the rest of the analysis, the idea is that we use this reduced template matrix for the entire analysis, and that helps us reduce costs by quite a bit. So what we were trying to do is, for one, we were trying to compare RSVD and SVD and see which is a better method. And secondly, we were also trying to implement it into the pipelines. So for example, in the next slide, so I tested it based on time, based on computational costs and overall efficiency. And in terms of all of these, RSVD performed much better than SVD. So we do think it's a better method. We do think it's something that can be used. So the main idea that we did or performed was we wrote up the RSVD code, we inserted it into an existing LIGO pipeline. So, and then we basically use that pipeline for analyses. So that's what some of us are working on right now. We're trying to do subsolar searches with this improved technique, and we think that might help a little bit. So that's that's what I was trying to do basically at some point.
So now that you've mentioned Sumedha, I was curious. So this is only in the online analysis detection pipeline, or is it also being used in the offline analysis too?
No, this is all offline. It's harder to do online.
Yeah. So do you think in the case of parameter estimation, even relative binning would be performing well, right? Then, because even relative binning can actually be mainly used for the inspiral part, where there are not a lot of characteristic features in the frequency, where almost the waveforms look similar as you were trying to describe.
Mm-hmm.
So, but this is for the detection purpose, and okay.
Yeah. Like parameter estimation works a bit differently. So, I mean, at some point I did bring this up with my supervisor. I was like, okay, what if we put combine RSVD and parameter estimation?
Exactly. Yeah.
But that's not as straightforward as it sounds, because I think with Bilby and the current packages that are used for parameter estimation, it's hard to sort of make them work with RSVD. So that would be a huge project in itself. I don't think it's impossible, but it's complicated.
Okay. That sounds really interesting. So, okay. So, Pratmesh is asking, how is the noise reduced in a given gravitational signal?
What do you mean, how is the noise reduced?
Yeah, Pratmesh, you can ask the question.
Hello.
Yeah, I can hear.
So whenever we detect a gravitational wave, there are some noises that get induced in the wave, like moving of a car beside a
Yeah.
or seismic noise. So how does it is reduced?
I don't, I'm not sure how it's reduced particularly, but the main reason that we use match filtering, for example, is because of that. So, for example, this is a very simple representation, but the detector data actually looks a lot more clustered, a lot more intense. So match filtering basically pulls out that one specific match over there. So that's usually what they do in terms of noise. But if you mean what people are doing to try and reduce the noise generally, that's there's a whole group within LIGO who's working towards that. And for example, like Kagra, the new detectors in Japan, what they try to do was introduce cryogenic mirrors, because when you're actually using the lasers and stuff, the mirrors within the detectors, they tend to heat up, and even that contributes as noise because it's so sensitive. So noise reduction in itself, in terms of seismic noise, quantum noise, whatever, all of those other things, that's a whole separate thing altogether. That's like the experimental side of LIGO. So I'm not sure if you're asking about that or if you're asking about how we pull out the signal from the noise.
Maybe it's referring to the PST that you people generally use.
Yeah, definitely. That's also a thing. You do have noise curves, so that is a check that goes through it. So, but again, modeling noise is a huge problem because it's so random and it's so chaotic. That's not as straightforward, I think.
But the ultimate takeaway is that people do look at the noise sources and model the noise, and they
Yeah.
do. Yeah.
Definitely. That is something that they're doing. They're also trying to use machine learning to do that, so that we can actually identify the noise curves beforehand. So some people are actually trying to generate and simulate the glitches that we see by glitches, glitches and, well, the noise, basically the noise curves, and then try to feed it into a machine learning program and try to work with that. But I don't think they've been super successful so far. Of course, it's not easy. It's a very big project in a sense.
Manvi, you can ask your question. Manvi.
Yes. My question is, do tiny gravitational waves generated by collision in stars dark matter problem?
So I didn't get the last part of your question. Sorry, can you repeat?
Yes, one second. Do tiny gravitational waves generated by collision in stars dark matter problem?
Okay, if you mean if we solve the dark matter problem, I don't know. I don't think so. I don't think it's that straightforward. Yeah.
Manvi, can you maybe try to be a little more like clear in your question, like what you're exactly trying to ask?
Yeah, that would be helpful.
So are you saying, well, will these tiny gravitational waves produced by collisions in the stars due to dark matter may be a problem and interfere the primordial black hole searches or something like that? Or what do you mean?
Yes, I mean that only.
Sorry. I missed that a little bit. Surendra, can you just repeat what you said?
Yeah, I think she's trying to ask whether these tiny gravitational waves that are produced by collisions of dark matter inside a star be a problem for uh, detecting these primordial black hole gravitational waves? Like, can
I
there
don't
be
think
degeneracy between them?
no, I don't think that should be a problem. No.
Yeah. Manish is asking, for match filtering, we would have data so that it got matched. but how the data we find out.
Sorry, what?
Yeah, Manish, you can ask a question.
Hello, ma'am.
Yeah.
Yeah. So my question is, you said that the match filtering we have done to find out the gravitational waves. So to match that gravitational wave, we need some data, that
Mhm.
initial data, so that it got matched to that gravitational wave. So how do we find out these that initial data so that we can match?
Oh, that's not the initial data. That's just the data that's coming into the detectors. So when LIGO and Virgo are operational, and the gravitational waves, sorry, whatever it's detecting, basically, that's the data that's coming in.
No, I
So,
think he's trying to ask the template bank. How is it created? Like you're
okay. So you
matching them
mean,
against existing waveforms, right? So he's calling them as
Yes, yes.
initial waveforms.
right? Okay, sorry. So the templates basically they come from various things. For example, I mean, very high up, it finally comes from general relativity, where you try to basically use the Einstein field equations and derive equations for maybe, okay, so if there are two merging black holes, what is the waveform? Sorry, what does the equation look like? And then subsequently, what does the waveform look like? And there are many methods to actually create those templates, but it comes from theory entirely. I don't know if that answers your question.
Yeah, actually you have answered. But I also one more question. So we have lot of gravitational wave templates like detecting as so far, but how we mean distinguish that gravitational wave is coming from that star or anything. So how we determine?
So do you mean this while we're doing match filtering, or do you mean generally?
No, that match filtering only.
So match filtering, the template that we have, that isn't specific to any star particularly. For example, maybe this template is showing you what a binary black hole merger of maybe 10 solar mass and 20 solar masses looks like. That's all we know. We don't know where exactly it's coming from. We just know maybe in terms of certain parameters.
I
So if
think
you do,
he's trying to refer to the extrinsic parameters and localization.
uh, oh, so that is more to do with parameter estimation then.
Yeah, yeah.
Okay, thank you.
I mean, if you really want that question to be answered, you can go to the day 5 and 6 talk where Ish has actually talked about these various parameters that a binary has, both intrinsic and extrinsic, and how one varies all these parameters across certain initial priors and gets the best fit. And from that, one can actually get the parameter estimation. That's how parameter estimation works, and from there we actually get the localization, distance, etc. to these sources. I mean, just to add to that, maybe I'm not taking too much time of Sumedha, but so you see the way the gravitational wave, it has some polarizations, right? So when it falls onto your detector and it's being detected, so the detected signal also depends upon at what inclination is this gravitational signal that is coming to the detector is at. So based on different inclination of this gravitational signal, you will have different observations made in the LIGO detector for the same given binary black hole based on the inclination and distance. So even those are some parameters that we need to find. So, okay. And the next question is maybe, yeah, Divyansh is asking, what can we say about primordial black holes in non-inflationary models of our universe, such as conformal, cyclic cosmology, or any other?
Didn't someone ask this already?
Yeah, he did. I think maybe you can just reiterate, like, what can we say about primordial black holes in non-inflationary models?
Um, okay, I'm not sure what you mean by just say something. There are formation mechanisms that are non-inflationary, if that's what you mean. Um, yeah, I'm not sure what the question is exactly.
And just try to unmute you. Divyanshu, you can go ahead.
Hello.
Yeah, I mean,
Okay. So my major question was that if we found I mean a primordial black hole, so do we ever have any certain kind of parameter that would help us to decide if it existed or it began when it was an inflationary scenario or a non-inflationary scenario? So if we detect a primordial black hole, can we further deduce that what was the initial conditions when it got created?
Yeah, that is something that you can technically do. It hasn't been done before, but it is something you technically can do with. So usually early universe cosmologists and inflationary cosmologists, they usually plot something called as the power spectral plot. Okay, sorry. But yeah, it is something that they do plot, and it is something that gives us an idea about what the formation mechanism basically. I'm not too sure exactly how they do backtrace it because, like I said, it hasn't been done before, but it is a possibility for sure. And also, additionally, I think it reflects, like if you were to detect something, it does reflect in the detection itself and the models that were used to make that detection. So you would also know something there. So for example, the example that I showed with the very simple test run that I showed, that was basically an inflationary scenario. So if we did detect something using those models, I could very confidently say, okay, this is from an inflationary scenario. Whereas if I chose a model with regard to these other non-inflationary scenarios, I could similarly comment that way. So that's also another roundabout way of going about it.
So Shubham is asking what information we're looking for early universe by this primordial black hole detection.
We could know a lot about how, those density fluctuations, for example, how structures came to be. So most of the structures that form, we know very little about the early universe, basically. There's just like a handful of things that we do know. So the idea, or the optimistic idea rather, is that once we actually detect something from the early universe, like primordial black holes, maybe we'll just have an idea about what the rest of that phase was like. So it's a very broad question in the sense because we know nothing at the end of the day.
Yeah. Any more questions, guys? You can either raise your hand or post them to the chat. I'll give you all 30 seconds, maybe. And thank you, Sumedha, for the wonderful talk. I do believe that people here who attended today learned a lot on primordial black holes and how to detect them using gravitational waves.
Yeah, thanks a lot for arranging this. This was really nice.
Yeah, a lot of people are saying great talk. Thanks a lot.
Yeah, if you have any more questions, please feel free to contact me. I think the details are on the GitHub page.